So now we're going to talk about the urinary system. The first thing we're going to talk about how the urinary system is one system of excretion, but it's not the only way that we excrete substances. We can also excrete some substances through our skin when we sweat. If you've ever had maybe a little bit too much whiskey and the next day you're working out and you feel like you smell like whiskey, you are correct. You are sweating out your whiskey. Obviously it's been metabolized, but yes. You are excreting carbon dioxide as a gas through your lungs. You are actually losing fluid across the epithelium of your lungs as well. You may have noticed on the previous section on the respiratory system that we do exhale moist air, so we are losing quite a bit of fluid through the air that we exhale as well. It's a source of dehydration for people like me who have to talk a lot. Let's see, liver excretes bile, and that is going to exit the body as part of feces, not exclusively feces. And then the rest of it is kidneys, nitrogenous wastes in urine. Lots and lots of fluid is lost through the urine. Things like ions, balance, pH, things like that all get excreted through urine. So they're the primary organs of excretion. They're the way that we're going to get rid of the waste products that are produced by metabolism. Now, the homeostatic capacity of the urinary system is incredible and also incredibly clinically significant. We're really just going to scratch the surface today. We're not doing everything. Body water levels are particularly important. So there's something that's going to be ins versus outs, in and out, I and O. So we're going to take in a certain amount of water and we're going to get rid of a certain amount of water. And it always has to be in balance. Regulating nitrogenous waste and other solute waste, pretty important. And it is the main function, right? We're trying to get rid of nitrogen. Nitrogenous waste comes from proteins, basically. So you eat a big steak or a big plate of beans. That has amino acids as the backbone, and the backbone of the amino acid is nitrogen, carbon, carbon. So that nitrogen, that is our nitrogenous wastes, that gets made into urea. Another form of that is ammonia. So ammonia and urea are closely related. So we do get rid of a certain amount of sodium, chloride, potassium, calcium, hydrogen ions, and creatinine is a big one as well. In different quantities, and it's going to be really dependent on the endocrine system. It's going to be influenced by a lot of hormones, what we keep and what we get rid of. But in addition to just getting rid of a bunch of stuff, your kidney's actually in charge of quite a bit. I mentioned that fluid balance, ins and outs, right? Now, the most important thing for blood pressure, the major way that your body has for controlling blood pressure and homeostasis is through blood volume. And the thing is, all this fluid in these different compartments, the fluid in your blood, the fluid between your cells, the fluid in your cells, it all came from the same place. It's just changing compartments. So when we adjust blood volume, we're adjusting blood pressure. When we pee, we reduce blood volume because that fluid from the blood left as urine. Or if we retained our fluids, we retained them in our blood, we did not pee that out, that increases our blood volume, that increases our blood pressure. So blood volume, blood pressure are basically going to be the same thing for our intents and purposes. We're going to have a lot of hormones controlling that. Among them, aldosterone is going to be a big one today. And ANP, that stands for, depending on which source you're reading from, atrial natriuretic peptide. That means that we have certain hormones that are going to make you pee more, like, let's see, make sure I don't get this mixed up. Aldosterone is going to help you retain water. You're going to pee less. Yes. And ANP is going to make you pee more. It's actually going to be one of the very few hormones that causes a reduction in blood pressure. My dogs are running around in my attic for some reason. I don't know if you can hear that over my speaker. It's very disconcerting when they're just up there tromping around. There's nothing up there. They just like it. Okay. They're wrestling. I just heard an aurora. Okay, so maintaining acid-base balance and blood pH. We mentioned this in the respiratory system as well. When you are breathing, when you're undergoing internal respiration. After cellular respiration, you have a buildup of carbon dioxide. You need to get rid of that carbon dioxide by exhaling it. There goes carbon dioxide. Because if you retain that carbon dioxide, CO2 plus H2O equals carbonic acid, which makes you more acidic. And I mentioned before that your acid-base balance, your pH range in homeostasis is very narrow. If you go too far out of that range, we call those conditions alkalosis and acidosis, and they can be very deadly very, very quickly. So we have not just the respiratory system controlling respiratory rate to get rid of carbonic acid, but we have our urinary system contributing to acid-base balance by, first of all, just peeing out acids. Metabolic acids get peed out as waste. But we're also going to have something called bicarbonate buffer system. So your kidney tubules, we'll see later, are actually going to synthesize bicarb and be part of a buffer system that can absorb some of those hydrogen ions and make them into a weaker acid, which you actually already know about. Okay, let's see. Blood cell production via EPO, erythropoietin. Your kidneys are going to synthesize erythropoietin. And that's part of your life cycle of a red blood cell. So we've done that before already as well. You synthesize EPO from your kidneys. The target cells for that are in your red bone marrow. You synthesize all of your red blood cells because of EPO. And that means that you have a recurring source of fresh red blood cells. It also is part of a metabolic pathway for vitamin D, so that's pretty important, especially on a rainy day like this one, that we have the ability to synthesize adequate vitamin D, which is also necessary for calcium absorption. Some of the anatomy of the urinary system, these are, of course, the kidneys, then these are the ureters. That goes to the urinary bladder. Those are actually going to enter the urinary bladder pretty far down. So if we saw the posterior wall here, we'd see the ureter opening into the urinary bladder way down here. And then there's a urethra that allows urine to pass to the external environment. We do have a couple of smooth muscle sphincters to keep us from peeing ourselves. So hooray for sphincters! The kidneys themselves are divided into lobes, and there's quite a bit of anatomy here. It obviously gets more serious when you get into a BIO127 course for what this anatomy actually is. So you're going to have parts of the kidney. There's a superficial cortex of the kidney and a deep medulla of the kidney. And in the medulla, you're going to have renal pyramids. Do we have columns labeled here? We don't. So unless we have columns labeled elsewhere, you don't have to worry about them right now. Okay. What we're going to focus in on are the nephrons. The nephron is the basic functional unit of urine formation. This is where we are making urine. We're taking fluid from the blood. We're going to filter it. It's going to go through a process of secretion and reabsorption in the rest of these series of tubes. And then it's going to be collected as urine in something called a collecting duct. So basically, you're going to have filtration. We're going to go from blood to something called filtrate out here in the cortex. And then we're going to synthesize that into urine, and it's going to be collected in collecting ducts that are radiating through these pyramids. This is going to be the direction of collection of urine. And we're going to go in through this structure. They're known as calyces, but apparently we're not doing that right now, into the renal pelvis, and that will lead to the ureter. So again, I mentioned cortex versus the medulla has the renal pyramid. Most of your structure of the nephron is out in the cortex. Only a couple of parts go into this pyramid. We have the nephron loop, and then the collecting duct makes it down to the, as I already mentioned, this is called the calyx structure. That leads to that renal pelvis. So we will delve into these individual components of the nephron. We're going to start with the glomerulus. I'm gonna, let's see, make sure I don't go overboard on this. So just look really, really close. Sure. So I'm gonna cover those two slides here visually for you. The glomerulus, and yes, you should be able to pronounce glomerulus, is a tufted capillary bed. The purpose of this capillary bed is not to oxygenate tissues. The purpose of the specialized tufted capillary bed is to filter. So it's going to have a slightly different structure than other capillary beds that we've seen before. At the microscopic level, we're going to have the ability to push a certain amount of fluid and some very, very small solutes out into a space known as the, this is very weirdly illustrated, glomerular capsular space. So here's your glomerulus, here's your glomerular capsule. Sometimes it's known as Bowman's capsule if you look at outside resources. So weirdly illustrated. Okay, so you are going to push blood into this glomerulus and it's going to get filtered, and a certain amount of fluid and solute is going to be filtered into this capsular space. From that point on, we call it filtrate. From there, that filtrate is first going to go to the proximal convoluted tubule. It is proximal to the glomerulus. It is indeed very convoluted, and it is a tubule. These are all tubules. From the PCT, we go to the nephron loop. Some people call it the loop of the nephron. Some people call it the loop of Henle if you go to outside sources. After that, we're going to go to the distal convoluted tubule. So that is a symmetrical term to the proximal convoluted tubule. It is distal to the glomerulus. It is indeed convoluted, and it is a tubule. And at that point, what we've gone through is a process of reabsorption and secretion. We've had some fluid exchange continuously between the tubules, proximal, distal, loop of Henle, nephron loop. We're losing fluid, we're losing solutes, we're gaining solutes, we're not usually gaining fluid, we're concentrating. We're taking a very dilute filtrate. We managed to get rid of a lot of fluid in this capsular space, in this filtrate. There's a lot of fluid, there's some solute. We want to get rid of a lot of solute, keep a lot of the good stuff, get rid of as much nitrogenous waste as we can. Anything toxic, anything bad, lots of drugs, we want out. We want this to go out, but we want to retain as much water as possible because we don't want to dehydrate to death. So that means that over the course of this nephron, overall, we're going to concentrate that filtrate into urine. By the end of this process, we will have concentrated it so much that urine is only about 1% of filtrate. We're going to reabsorb 99% of what made it into Bowman's capsule over here, the glomerular capsule over here. And we did so because of this close connection between the tubule system and the peritubular capillaries. Now let's make sure that I caught everything. Glomerulus, capillaries where filtration occurs. The glomerular capsule, also known as Bowman's capsule, receives the filtrate. The PCT, we are going to have a certain amount of reabsorption of water and nutrients into the capillaries. Reabsorption is a specific term. Reabsorption specifically means that we went from the tubule to the capillary. The opposite of reabsorption is going to be secretion. Secretion specifically means that we went from peritubular capillaries to the tubules, which makes a certain amount of sense. If it's in the tubule system, it's going to get peed out. That's its destiny, is urine. So secretion means to the tubules because that's going to be excreted. That's going to be pee. Let's see, in the loop of the nephron loop or loop of Henle, sometimes I say nephron loop of Henle, both water and sodium and chloride are going to be reabsorbed. What we're going to find is that where water goes, water follows. Where sodium goes, water follows. Remember osmosis. What's our main rule of osmosis? Where does water go? Water goes to stuff. Sodium is stuff. So we did that like probably around day 1, right? We started talking about gradients. We started talking about osmosis really, really early on, and this is a big part of why. So sodium is going to be reabsorbed first. Water is going to join it via osmosis. That's going to be the rule, and we're going to see that a lot. And meanwhile, where sodium goes, chloride also follows because we have an electrical gradient. Very positive sodium goes, and chloride, being negative, is going to be drawn to that positive. So sodium goes, then chloride goes, and then water leaves via osmosis. That's going to be the general overview of the loop of Henle. And then the distal convoluted tubule, we have some tubular secretion. We are simplifying here. There's reabsorption across this entire length. There's secretion in both the PCT and DCT, but we're keeping it simple for BIO127. This is a beast in BIO212, I believe. It's a good beast, though. Everything in this is clinically relevant, and if it weren't, I wouldn't teach it the way that I do. Now again, blood volume is very related to blood pressure, and the kidney is very tied up into all of that. So one of the forces that actually drives filtration is blood pressure. So remember our lecture on the competing pressures in a capillary bed. So you have your capillary, you have a certain amount of blood pressure pushing fluid out, and you have a certain amount of osmotic pressure pulling fluid in. Those same forces are at play in the glomerulus. So you do have something called net filtration pressure working on the glomerulus, but here you have something called fenestrated capillaries that allow molecules of a certain size to leave, easy access for water to get through, and then you just have a certain amount of blood pressure physically pushing fluid outside of this capillary. So if you have higher blood pressure, then that arrow gets a lot bigger. If you have lower blood pressure, then that force gets a lot smaller. Therefore, if you have very, very low blood pressure, dangerously low pressure, one of the things that it can do is reduce kidney function. I think we're okay here. Let me know if you don't understand peritubular capillaries. These actually have a specific name known as vasa recta if you go to an outside source. We've made the nephron more linear. In real life, this is wrapping around itself. We're going to see something later known as the juxtaglomerular apparatus, and that means that the distal convoluted tubule is in physical contact with these specialized arterioles over here closely associated with the glomerulus. But this is artificially stretched out to be linear. Now again, for our oversimplification purposes, we'll have tubular reabsorption at the PCT and tubular secretion at the DCT. That is simplified almost too much. We have glomerular filtration only in this structure here. There's a lot of different names for what's going on. I want to make sure it's the renal corpuscle is the whole thing. If you take the glomerulus and the capsule together, it's the renal corpuscle. So filtration is only happening into the capsular space. There's no filtration here. There's no filtration here. There's no filtration here. It's not happening anywhere but here. Filtration happens from the glomerulus into the capsular space. Full stop. And that's why that product that's in that capsular space is known as filtrate. By the time that filtrate goes through the series of tubes and is in the collecting duct, now we refer to it as urine. And urine is what gets excreted. So a few more details, and I think I'm going to work pretty hard on your worksheet this week to make sure that the depth to that we're going to is going to be very, very clear. So I would use this lecture in conjunction with your worksheets to figure out exactly what depth we need right now, because this gets much, much deeper when we get into an actual A&P class. The question is, how much of this do I want you to know right now? So, I mean, I know this whole process like the back of my hand because I've taught it a million times. There's a really good comprehensive video on YouTube, Biomed Sessions with Ruz, R-U-Z. She's a Londoner. She's British. She only does it for the urinary system. She stopped. She probably got too busy with medical school. It's a really good explainer on everything related to urine formation. She's got one that's just about the glomerulus and filtration. She's got a nephron overview, which is the one I recommend for this. And then There's something specific to the loop of Henle that is really a bit too much, but that nephron overview has all of this in very, very wonderful, clear, excellent detail. So I'll walk you through this, but again, I am going to decide when I get to the worksheets what I'm really going to hold you to. So during glomerular filtration, as that blood pressure exerts pressure onto the fluid and pushes fluid from the blood into the capsular space, we do lose water, glucose, amino acids, salt, urea, uric acid, and creatinine into that capsular space. Now remember, we need to reabsorb a certain amount of that. So especially in the PCT, that first part, we're going to reabsorb immediately a whole bunch of that water, glucose, amino acids, and salts. Hi. The dogs got done playing up in the attic, so they're going to come and say hi. They had a lot of fun just romping around on their own, so that's good. I'm glad they can entertain themselves on a rainy day. Yeah, yes, it's very mature of you, entertaining yourself. Okay. Now, again, secretion means that the peritubular capillaries are actually releasing more stuff into the tubules after filtration has already occurred. We're not done getting rid of waste. So we can secrete more uric acid, more creatinine, more hydrogen ions, more ammonia, and not just penicillin, drugs in general do get secreted. So we filter some drugs, but we also secrete some drugs. And particularly the PCT is a place where a lot of secretion of certain drugs does occur. So that's kind of important too. We do reabsorb a lot of water. Most of the water, 99% of the water, is going to be reabsorbed across this nephron, and it's in general going to be following salt. So all of the salts, all of the sodium and chloride that we reabsorb is going to set up the gradient that, okay dogs, set up the gradient that pulls water, that creates an osmotic gradient and pulls water and invites it in. Finally, we're going to excrete, which means we are going to pee out ammonium, which is metabolized urea, salts, water, uric acid, urea, and creatinine. I think the only thing we haven't talked about in some way, shape, or form is creatinine. And creatinine is related to protein intake. It's a form of protein, and your muscles will use it as an alternate form of ATP synthesis. It can actually donate a phosphate group to ADP. And sometimes people supplement with it as well. So there's a good reason for it to be on this list. We have a lot of tests related to kidney function that test creatinine. They can be messed with. You can get false results if somebody's supplementing creatinine. Some of those levels change if you've even just had a big steak dinner. So we do have multiple kidney function tests, and that's what a lot of this is playing into. A major test of kidney function is glomerular filtration rate, or GFR. So there is a good reason that we're learning a lot about glomerular filtration, even at this level. Let's see. You know what? Actually, so far, and again, I've been lecturing and having meetings all day today. Worksheets. That's the word I was looking for. If my worksheets say otherwise, ignore the statement, but for now, I actually like everything in this column right here. It's all pretty important, and it's still minor compared to what we're going to be doing in BIO127. So for now, until I look at this again later when I'm writing a worksheet about it, for now, for the time being, all of this is pretty important. We said all of that. Yep, we said all of that. Hi, dogs again. Hello. So I did mention this, and luckily, while we were on this slide, I did mention that not just penicillin is being secreted, other drugs are being secreted as well. So some other secreted substances, penicillin, cocaine, marijuana, pesticides, preservatives, hydrogen ions. That means acid-base balance is partially controlled by just peeing out acid. Ammonium and potassium. Good. Now, one important thing specific to the nephron loop is the specific order in which we're losing sodium chloride reabsorbing sodium chloride and reabsorbing H2O. We have two limbs of the nephron loop. We have the descending limb. So we go, again, PCT to the nephron loop. When we go from the PCT into the nephron loop, that's our descending limb of the loop of the nephron. As we go back up towards the DCT, the distal convoluted tubule, that's called the ascending limb. So they're in order from PCT to DCT. This is the descending limb, this is the ascending limb. This is going to be also known as the thin limb, and this is the thick limb. And it's about the epithelium. This is a simple squamous epithelium. This is a simple cuboidal epithelium. So it does histologically have a thicker appearance. And that is all related to function, because in this side we do have some active pumping in that epithelium of sodium and ultimately chloride, and we've got some potassium. We've got some sodium potassium chloride pumps in there. We're not doing that right now. I just remember that sodium potassium ATPase pump we used to talk about back in the day. He's all over and he's really important clinically. We have a lot of drugs related to the pumps that are in this right here. They're called loop diuretics, if you've ever heard that term. If you haven't, ignore it. I hope somebody had a light bulb moment just then. Okay, so you have some pumps actively pumping out sodium, and then chloride follows into the interstitium. And that makes the interstitium of that medulla of the kidney salty, literally salty. Kidneys are salty because of these pumps in the ascending limb of the nephron loop. Because it's salty, that is what is exerting osmotic pressure on the thin limb. The descending limb with its simple squamous epithelium, the thinnest epithelium you can possibly have, water will eventually leave because it can, because there's a sodium gradient exerting osmotic pressure on it. So if this ascending limb were not pumping sodium, it would not be salty, and there would be no osmotic pressure, and we would not reabsorb H2O in the descending limb. If we don't reabsorb the H2O, it stays in the nephron. If it stays in the nephron, we pee it out, we excrete it. Peeing more, a diuretic makes you pee more. An antidiuretic makes you pee less. Loop diuretics. Okay, it's okay, we're not doing loop diuretics right now. I just want to show you that there's a good reason to learn this. That saltiness also exerts osmotic pressure on the collecting duct. The collecting duct is the last place where you can reabsorb any water. And sometimes it's going to be permeable to water, sometimes it's not going to be permeable to water. That's under a hormonal influence, but I don't think we're doing ADH today. So you can reabsorb water in the collecting duct in certain scenarios. Leave it at that today. In addition to simply peeing out hydrogen ions, you are also synthesizing bicarb through the simple cuboidal epithelium of your tubule system, which is pretty cool. So this bicarb, as we saw earlier, is in a sort of system. It can bind to additional hydrogens and become carbonic acid, which is actually a weak acid, or it can release hydrogen ions and make the environment more acidic. So that formula just goes back and forth, reabsorbing and releasing, and binding and releasing hydrogen atoms as needed depending on the acid-base balance of the blood. Pretty cool. I mentioned the juxtaglomerular apparatus. We had artificially stretched out our nephron and made it orderly, put it in order. That's not real. In real life, here's the PCT, here's the nephron loop, here's the DCT. That DCT is in connection with the arterioles that supply the glomerulus right here. So this is the juxtaglomerular apparatus. It does some important things related to GFR. We're not focusing on those right now. What we're going to talk about for this is called the JGA, juxtaglomerular apparatus. What we're going to use from the juxtaglomerular apparatus are some very special cells located right here that synthesize renin. So it's actually not the entire JGA, it's cells, specific cells, they're interstitial cells of the JGA that release renin. But renin's in a really important pathway, such an important pathway. There's a game I play when I'm teaching this. At my old school, I almost always, when I'm teaching this, there's usually a class next door that's taking one of the later classes in the program. And one of my favorite things to do is walk next door to people who are in, second year, third year of their nursing program and say, hey, are you going to use the renin-angiotensin-aldosterone system again? And they all go, yes! And so then the people I'm currently teaching the renin-angiotensin-aldosterone system to go, oh, I actually do need to know this, and I need to know it for the long term. It's a really important system. It's in control of blood pressure. And I've already mentioned that your kidneys are in control of blood pressure just by how much you pee, but there's multiple other ways that your kidneys are involved in blood pressure, and this is one of them. So the juxtaglomerular apparatus releases renin. Renin's going to act like an enzyme, and it's going to convert something called angiotensinogen into angiotensin 1. Now, angiotensinogen came from the liver. The liver synthesized angiotensinogen. The JGA in the kidneys released renin, converted angiotensin into angiotensinogen into angiotensin 1. If you're lucky enough to have the enzyme ACE, angiotensin converting enzyme, which was made in various capillaries, but mostly in the capillaries of your lungs, released ACE. In the presence of ACE, we can convert angiotensin 1 into angiotensin 2. And angiotensin 2 actually has 4 mechanisms. One of those mechanisms is that it's going to act like a hormone, and it's going to cause the adrenal cortex to release a different hormone known as aldosterone. I do have a way to break this down for you. I have a very, very simple version that I like to start with. Let's do a very, very simple version. Now, I learned this as RAS. This is starting from angiotensinogen from the liver, and it's kind of messing up my flow a little bit, but we'll deal with it. So, renin, angiotensin, aldosterone system. Renin is from the kidneys. Angiotensinogen is from the liver. Aldosterone is from the adrenal glands, and it's a system. Now, we do need to continue this. That's not quite enough, right? It's not quite enough to get what we need to. This is a pretty decent flow chart. I have my own way of doing this flow chart. Every time I do a flow chart like this, the kidney is way too big for that liver. Livers are way bigger than kidneys, just quick FYI. Not that I really want to actual size these, but whatever. So again, liver, angiotensinogen. And you do have to say ogen, angiotensin ogen, enogen. Kidneys, release renin. Because of this, we have angiotensin 1. Because of ACE, we have angiotensin 2. I am doing this terribly, I'm sorry. Angiotensin 2. And angiotensin 2 does 4 things. And the one we're caring about right now is aldosterone. Aldosterone is going to go and target the kidneys again. It's going to cause, make sure I say this the right way. We're going to increase sodium reabsorption, which is going to create an osmotic gradient, which means we're going to increase H2O reabsorption, which means we're going to pee less, which means we're going to have a higher blood volume, which means we're going to have a higher blood pressure. So the renin-angiotensin-aldosterone system ultimately is going to increase your blood pressure. It's an important system to know about because we have medications for basically every step of this system. Have you ever heard of an ACE inhibitor? Yeah. It also means that if you have kidney failure, your blood pressure is going to be awful. It actually elevates. It's going to be very, very high. You're going to have a hard time getting rid of a lot of fluid. and you're going to have a hard time managing a lot of solute balance. So when we do things like dialysis, we can control some of the fluids, some of the waste products, some of the ionic balance, but we can't. Dialysis doesn't take care of the hormones. It doesn't take care of EPO, and it doesn't really take care of renin. So there's going to be different mechanisms around clinically to deal with the other functions of the kidneys aside from the dialysis aspect. I mentioned aldosterone does 4 things. The other thing that aldosterone does, are we going to address any of that? Are we addressing any of it? We're kind of not addressing any of the other things aldosterone does. It also causes vasoconstriction. It makes you drink water. And what's the other one? I can't remember the other one. Oh, ADH. ADH is going to be a lot like aldosterone, so don't worry about ADH. We're not doing ADH today. Okay, so blood volume increases, blood pressure increases. There you go. So I think the last thing we're doing is comparing and contrasting the female urinary tract to the male urinary tract. And there's some important anatomy. Our last topic that I'm actually going to cover in BIO127 is going to be the reproductive system. So we may as well connect this idea a little bit into the concepts of the reproductive system. So one of the things I do when I teach reproductive is count the holes. Female reproductive and urinary system and the digestive system. The urinary bladder is most anterior. That urethra has a urethral opening. That's one hole. The vagina is a separate hole. And then the rectum is a separate hole. 3 holes. Male urinary tract. There's going to be a shared pathway in the urethra for both reproductive functions and urinary functions. So those testes are going to have a path that joins up at something known as the ejaculatory duct, right about there, not illustrated in this picture, so that both ejaculate as well as urine will pass through that urethra. So there's just the one hole for those 2 functions. That's the urinary bladder, and immediately posterior to that is the rectum. That anus means 2 holes. Okay, so make sure you understand anterior to posterior relationships in this as well, and that'll set us up for our last topic of reproductive as well. I imagine you're going to need to see this a few times. Again, if you're confused about the nephron, I recommend overlearning, overexposing yourself to it with biomed sessions with Ruz, R-U-Z. They're just very good. Honestly, I learned more from her than I did from my undergraduate experiences with the urinary system. I teach it almost exactly the way she teaches it when I'm doing it at the undergraduate level. So, highly, highly recommended. Let me know if you have any questions, and I hope you have a good... At the time of this recording, we're going to be going on break shortly after this recording.